Alright, so now that we made our model, it's time for us to plot our data so we can look at it visually. So what we're going to do first is make a figure that is going to let us plot. And next we want to add to that figure, so let's add trace. And since we have three dimensionless numbers, we're going to have a three-dimensional graph. So scatter 3D with our x values being our Reynolds numbers, our y values being our Schmidt numbers, and our z values being our Sherwood numbers and the experimental numbers we made. We're going to store these as markers, so we'll say mode equal to markers. Let's check out how that looks. Alright, so here's our initial plot. These markers are kind of big, they're all overlapping with each other, so that's one thing I kind of want to change right away. And I think I'm going to make the color vary with an increasing Sherwood number, since that's like what is alone in our relationship. So we can do that in this first line, so we can just do marker size, and we'll go with size 3 and check out how that looks, and then we'll go marker color. And if I want it to vary with the Sherwood numbers, I can just say marker color equals Sherwood, and Python will vary it with that variable. So let's take a look at that. Alright, so that looks much better. So we can see all our data points that we made earlier in the code, and now the color is changing with an increasing Sherwood number, which I just think that kind of looks nice rather than them being all one color, and it'll also help the lines of our models stand out when we put that in. So speaking of the lines to our model, let's get started on putting those in. So what we're going to do first is we're going to make arrays to store values for our Reynolds number and our Schmidt numbers. So we're going to do this with meshgrid, so np.meshgrid, and let me type this out and I'll kind of explain what this is going to do. So we also want evenly spaced values for both our Reynolds number and our Schmidt numbers to create our model lines. So as I said earlier, the Reynolds numbers are from 2,000 to 35,000. And we'll just do 20 lines. And then same thing with our Schmidt numbers. We will do 20 lines because we need the same amount of data points. Space. And that is again good from 0.6 to 2.5 and 20 lines. So what this mesh grid is doing is since I have the Reynolds grid first and the Schmidt grid second, the mesh grid is actually making arrays of it's going to keep the Schmidt grid constant, and it'll have an array of all the values in the Schmidt grid being 0.6, and it'll actually do each of the 20 values of the Reynolds number, and then it'll have another, and it'll pair those two numbers. Then it'll do the next value of the Schmidt grid, and it'll pair it with all 20 values for the Reynolds grid again. So I can kind of, well, let's first run it to make sure I don't have any errors. And then here, you can print out the Schmidt grid to kind of demonstrate. So see, we have our first element in the multi-dimensional array being 20 0.6s. And then the next one is 20 0.7s, and so on. And then if we look at our Reynolds number, which is, or our Reynolds grid, we have 20 numbers, except it's all 20 evenly spaced numbers from 2,000 to 35,000. So now it's paired these 20 numbers all with the first Schmidt grid number value of 0.6, and it'll allow us to make a line along these points. So since we're graphing in three dimensions, we obviously need our third variable. So that's going to be our Sherwood grid. And what we're going to do for the Sherwood grid is we have our model that we just made, or that we just calculated by finding the constants in the relationship equation. So we have Sherwood grid, and I believe the name of my array of the parameters was B. So we have Sherwood grid, and we're just going to use the model. So Sherwood grid equals the first constant. And actually the first constant was, remember, it was the natural log of the constant in the equation. So we're going to do NP dot exponential of the first element, and then we're going to multiply that by the Reynolds grid to the power of the second element in our parameter array. And we're going to multiply that by the Schmidt grid to the power of the third element in our parameter array. So shift enter. Alright, no errors. So we made the grid of all the points for our line, and now what we actually want to do is put them together so we can put the line on the chart. So we'll do that with a loop. So for I, then we'll go I2 and I3 in zip RE grid. So with this zip function, we're going to use this zip function, and what this is going to do is it's actually going to have a separate counter for each Reynolds grid, and Schmidt grid, and Sherwood grid. And it'll kind of allow us to put these values from each of the arrays together into like a point. And then we can add, or not into a collection of points, and then we can add a trace, a line trace along along those points to get our model onto the chart. So we'll do fig.add trace, and I always forget the underscore. So fig.add trace and graph objects.scatter 3D. And we're going to say our x, again, is, since I is now paired with Reynolds grid, x is I, y I2, and z is equal to I3. And this is going to be mode, as I said, what this is making our line, so mode line. And we'll go line color of gray, just so it's different than the points, the markers we made earlier. Let's check this out. Alright, so no errors, but let's check our figure out and see what it looks like. Yep, so here's our first section of the line. So as I said, this is changing our Reynolds numbers and our Sherwood numbers, but it's each line only has one constant Schmidt number. So obviously this isn't a grid, so it's not giving us too much information yet. So we want to add all the lines going the other way so we can actually see a trend with looking at all three different dimensionless numbers. So we'll do that pretty easily. All we're going to have to do is just switch around our mesh grid, which values we're keeping constant. So I'm going to copy and paste this whole thing. Go down here a little bit, paste. So we want to keep the Reynolds grids as constants paired with all the different Schmidt grid numbers now, so we'll switch that. We also got to switch where we assign the values. Alright, so we've switched and we now have Reynolds grids being constant and paired with all 20 values of the Schmidt numbers. And then Sherwood grid should stay the same. Our loop we can actually keep the same since we're changing the grids up here. Now let's shift enter, run it. Alright, all good. Let's check out the figure again. Alright, and we have a grid. And this grid is using our model, the model coefficients that we just found for the relationship earlier in the code. And we can see that it follows our data pretty well, and it'll help us predict, or help us if we want to like predict other values for different values of the dimensionless numbers. So now what we have left to do is just kind of some like convenience changes of the model, or visual changes too, like this legend over here. We don't really want to keep that here because it's tracking all of these lines. We also want to label the axis titles, so we can do that with one more function. So we'll do fig update layout. And the first thing, I'll change the height and width. So we'll say height want to be 800, and width we'll also have it be 800. Next, we're going to want to get rid of the legend. So show legend, we can just set equal to false, and this will stop it from showing the legend. Next, we want to name the axes what they are actually called. So say scene equals date, and then we can name each axis title. So x-axis we'll start with is the Reynolds numbers. Our y-axis is our Schmidt numbers, and our z-axis title is our Sherwood numbers. So let's shift enter. Hopefully we have no errors, and that popped the figure up for us. So let's take a look. So yep, we have our Reynolds number, our Reynolds axis labeled from 2K to 35K value-wise. We have our Schmidt axis labeled, and we have our Sherwood axis labeled. And as we can see, this three-dimensional graph allows us to look at our data and see how it'll change using our model that we did with our simulated experimental data, and we can see how the data should change based on the different dimensionless groups.